Maybe you introduce yourself. Okay.
I'm from Algarve. I'm in Sydney only for 11 months, 25 days. So I cannot speak about the past. I don't have photos to show of past activities. I have to speak a little about the future. So I speak about primordial gravitational waves and to try to answer the question if it's possible to detect them and how far in the future this will happen. Today, Zalem was saying that he waited 35 years for the detection of gravitational waves, and he ended this slide saying that he's very eager to see these primordial gravitational waves because it will give an echo from Big Bang. So how long we have to wait for this detection? Direct detection, I mean. So, just initial slides. We are here to commemorate the first detection 10 years ago. In 2015, we detected a merger of two massive black holes. It was the first detection. It was already said that it was another test of general relativity, which it has a distinction. But it is also important because it opens a new window on the universe, and in particular to the Big Bang. So, to date, about 300 gravitational events were detected. Most of them collisions of black holes. I think most of you are most interested in these sources of gravitational waves. But there are other sources. For instance, we have supernova, we have rotating neutron stars, and of course, inflation in the universe. I will focus on this one. This is very important because it's the only way we can look directly to the Big Bang. Gravitational waves can live in principle, we call it background radiation, and we can detect them. But the only way to see directly is through gravitational waves, because the universe was opaque to electromagnetic waves and also to neutrinos or cosmic rays. And the only way to see it's through gravitational waves. And it's also important to see because they can give insights in physics of high energies, in fact, ultra-high energies that are beyond the reach of particle accelerators we can build on Earth. So, if they are so important, the question is it possible to detect these primordial gravitational waves? So, gravitational waves are generated in an expanding universe. So if the universe was static, as at a certain point Einstein thought, there would be no generation of gravitational waves. But since it's expanding, there are gravitational wave generation, and we can find the corresponding spectrum. One way of doing that, one I use, is to use the formalism of continuous Bagaduov coefficients and specify a model for the universe so that I can produce the full spectrum, continuous spectrum, from ultra low frequencies to the maximum frequencies. So let's illustrate this with an example. So it blocked.
It's working now, but I think you've gone too far.
It's already. Example, I consider two-scalar cosmological model, which I proposed a few years ago, that unifies inflation, dark matter, dark energy under the same roof. So this theory has two fields. One field plays the role of inflaton, and later on of dark matter, and another field plays the role of dark energy. This model has also two parameters, alpha and beta. They are free as theoretical parameters, but they are constrained by cosmological data, and they are constrained to these values with these error bars. And if this model has these parameters with values lying in these intervals, then it is consistent with cosmological observation. It's distinguished from lambda CDM in that sense. So, using this model, and using the formula of Bagaduov continuous Bagaduov coefficients, we can calculate the number of parameters produced as the universe expands. So I just show you a graph. Here we have the number of gravitons. Here is timing, number of e-folds. Here is the start of the inflation period, inflation, then transition to radiation dominated, then radiation dominated, and here dark matter dominated and dark energy dominated. As you see, most of the gravitons are reducing during inflationary period, also a few here in the transition to radiation, and then a few more here in dark, in matter dominated and dark energy dominated. So since most of them are produced in here, we can call these gravitation waves primordial, although there is small evolutions here, most come from here. So now we can translate this result into full spectrum. I'll show the full spectrum here. So it goes from ultra low frequencies to maximum allowed frequencies, corresponding to the wavelength equal to double distance today and double distance at the beginning of inflation. We have here a continuous spectrum of gravitational waves. This was obtained for the central values, but if we consider the error bars here, all the spectrum fit inside this envelope here. So we know that it's somewhere here in this region, all the possible solutions corresponding to the cosmological data. And here we have the sensitivity of Planck's detectors. We don't see here LIGO or Virgo or carbon because they will just be here above, so it's much above. So to reach this curve here, we need next generation detectors. LISA and the Cosmic Explorer Einstein telescope are not enough. So this will be the next step. In 10, 15 years, these detectors will be operational, we hope. But nevertheless, they will not have sensitivity enough to reach this primordial gravitational wave spectrum. So we'll need to wait for the next generation, DESIGO and BBO. So DESIGO is a Japanese project that is under the pre-development stage. Maybe in 10 years or so, they will launch a probe, be DESIGO, will test the technology, and then maybe 10, 15 years later, they will go to the ultimate or the final DESIGO. BBO, it's more an idea than a project. There's no investment, there's no people doing research or developing it. It's just an idea that arose 20 years ago, and since then, it has not received financing. So we'll have to wait a lot of years till we have these detectors operating, and then we may hope to detect this primordial gravitational waves. Now let's go here to lower frequencies. Here it's not a detector of gravitational waves. It's a way of indirectly detecting it using pulsar timing. So this SKM will be operational in a few years. And in fact, it can mimic gravitational detector the size of the galaxy using these pulsars that are very precise clocks. So as you see, this sensitivity curve just barely touches this, so I don't think it's very hopeful that you expect STA, the first version, to see gravitational waves, primordial gravitational waves. So I think it's possible to detect, but we need to wait next generation of gravitational waves detectors, ground-based or space-based, in order to achieve this. And meanwhile, I think it's worth investigating this area, because when these gravitational waves will be detected, there will be valuable information about the very early universe that we cannot achieve by other means directly. So it's very difficult, but the price is also very high, so it's worth investigating or spending time in it. Thank you.
Very much, Paulo. So actually, the area of cosmology was an area that early on in the history of GRAB was present. We had João Rosa. He developed this area, warm inflation, some very noticeable results. I myself worked in cosmology many years ago, so it's great that now with Paulo we have people working more in cosmology, which relates to the next talk very nicely, which is the high energy physics. So this was not an accident, of course. So Antonio,